Okay, so we've defined first-order Markov processes. We'll now see how to generalize these to what are called second-order Markov processes. And in fact, this will be a very straightforward generalization of what I've just shown you. So the task, again, is to model the joint distribution over a sequence of n random variables. And in a second-order Markov process, we make the following assumption, that this joint probability is again a product of terms. We have the probability that x1 equals little x1. We have the probability that x2 is equal to x2 condition on x1 equals x1. But then for elements further along in the sequence, I equals 3 to n, the value for the ith random variable depends on the previous two random variables. So remember, in a first-order Markov process, we would have had this term alone being conditioned on. We now also add the term 2 positions back. So this, in a sense, is a slightly more powerful model in that it can capture a broader class of distributions. We're conditioning on a little bit more information, but we're essentially just conditioning on the previous two elements in the sequence rather than the previous one. So if we condition on what the previous element, just I minus 1, it's called a first-order process. If we condition on the previous two elements, it's a second-order process. And you can go further. You can, in fact, define third-order and fourth-order Markov processes in the natural way. So that's essentially it. That's a second-order Markov process. To make things a little bit simpler, these terms are a little awkward. To make things a little bit simpler, we're actually going to write down a second-order Markov process as follows. I now have a product from I equals 1 to n, and at each point I have the ith value conditioned on the value at I minus 2 and also I minus 1. And I'm now careful to essentially define a couple of random variables, x minus 1 and x0, essentially at the start of the sequence. And these random variables always take the value star. So you can think of us as always starting this Markov process with x minus 1 equal to star, x0 given star, and then we have x1 as the next element, maybe that's some word there, x2 is the next element, and so on and so on. Okay, so this just makes things slightly simpler, basically from a notational point of view. So up to now, I've assumed that the length of the sequence, n, is fixed. But really, we'd like to generalize this kind of model so that the length of the sequence, n, is also a random variable. What this means is we'd like to define a distribution over all possible sequences where the sequence length can also vary. And you can see now how we're getting closer and closer to the language modeling problem, because with language models, it's essential to model a distribution over sentences where the length of the sentence can vary. And there's actually a very simple solution to this, a direct extension of second-order Markov processes, or first-order Markov processes for that matter. And we'll essentially just say that the nth random variable is always equal to stop, where stop is a special symbol. It's special in that it is not in the regular vocabulary in the Markov process. It's not a member of the set V. It's sort of an additional symbol, so it's not in the set V, and it's only ever seen at the end of a sequence. And then we can use a Markov process exactly as before. We can say that this joint probability is equal to a product of terms, I equals 1 to n. At each point, we condition the value for the ith random variable on the previous two random variables. And we're just assuming that xn is equal to stop. So we now have a way of writing down the probability of a sequence for any length. We get a distribution over all length sequences. Intuitively, what's going on here is that I have a process where at each point I'm generating the value for the ith random variable conditioned on the previous two random variables. So you can think of generating a sequence of random variables in left to right order, first x1, the next 2, the next 3, up to xn. And at each point, there's the possibility that this ith random variable will be stop. And if I see the stop symbol, I then just stop and output that sequence as the output of this process, this sampling process. A little bit more formally, you can show that under quite mild conditions, we do, under this addition, under the stipulation that this is equal to stop, we will have a well-formed distribution over all possible sequences of varying lengths. And I don't want to go into the details of that, but that's a fairly straightforward application of the theory behind Markov processes to show that we have a well-formed distribution. But again, the main thing is just to think about the intuition, where at each point we're generating some symbol, xi, and if we ever generate stop, we immediately terminate the process.